Good afternoon, folks. We're just going to wait a couple of minutes for the top of the hour, and then we'll get started. All right, we're at the top of the hour. I'm seeing the attendee list grow a little bit as we get started. So good afternoon, everyone. My name is Eric Eula. I'm the Director of System Operation and Market Design at ESIG. Here to help moderate today's webcast. Welcome, everyone. Those of you not familiar with ESIG, ESIG is a membership-based nonprofit organization that provides objective information, different resources and reports and networking opportunities in support of clean energy and integrating emerging technologies onto the power grid and the broader energy systems. We do this through workshops, tutorials, webinars, blogs, as well as through our working groups, users groups, and task force activities. And through those, we produce technical resource materials such as reports, like the one that we'll be talking about today, and fact sheets and other types of products that we share with our members and with the public. So those of you that are ESIG members, thank you for your support. It makes these webinars possible and all the other work that we do. So our workshops and monthly webinars are open to everyone. So please feel free to share these with colleagues in other organizations and elsewhere. So feel free to register these whenever you see them. Also, make sure to keep up on LinkedIn, YouTube, Facebook, and Twitter, including on YouTube, where a lot of these webcasts do go after we record them. A couple logistical matters before we get started. So participants are muted for the webinar, so don't have any audio questions as part of this webcast. Instead, we'll have the Slido platform as we normally do for these ESIG webcasts. We request that you ask your questions through the Slido platform, and when you go to the site, we'll add that to the chat when we get a chance, at slido.com, and you'll be entering in ESIG 16 as the event code, and through that you can ask your question, and there's also opportunities to upvote questions that you see that you'd like for us to get to first, and we'll kind of go through those at the end to make sure that our speakers get a chance to respond to those. Reminder also just to be respectful with your questions and also to prioritize posting questions for the speakers and rather than personal statements or opinions that you'd like to share. It's always good to have those as questions. So say about 10-15 minutes for Q&A at the end, and we'll share additional responses to those questions as well as the slides afterward. All right, so resource adequacy assessments are the critical exercises to ensure that systems have sufficient resources to meet conditions of the future, meaning peak demand, as well as other critical time periods, such as combined low renewable output with high demand and extreme weather conditions. So while resource adequacy assessments are performed regularly for different planning regions across an interconnected system, They often assume imports and exports during those critical time periods that can affect what their adequacy needs are for their particular system. They are performed somewhat independently for each region. So a wide area resource adequacy assessment, including assessments that are interconnection-wide, or maybe in the case of the United States, even US continental-wide, can improve efficiency and reliability and of the potential interactions across those regions. This is particularly true when the assessment has a consistent framework for the weather data, scenarios considered, and metrics used across the footprint. So this is the main focus of and conclusions of a recent ESIG report that was put together by the ESIG Redefining Resource Adequacy Task Force that was published just this month. So in this webcast, we plan to share key findings of that report and the task force discussions, including things like scenario-based planning, interregional transfer capability that are used as part of these assessments, and the use of consistent data across the entire wide area footprint for these improved assessments. So we have two speakers, both from Telos Energy, who were the lead authors of that report that I mentioned, as well as the task force chairs of this task force that will speak to you today to share some of the key findings on the report. Derek Stenclik is the founding partner of Telos Energy, and Aaron Schwartz is a senior engineer at the firm. So I'll hand it off to Derek in just a bit. Just a short reminder again to use Slido, slido.com with the ESIG 16 code. Yeah, I guess with that, let's go ahead and get started. So I'm going to turn over to Derek, and Derek's going to share his screen and kick us off.
All right, thank you very much, Eric, and thank you all for joining. I'm going to share my screen, and we'll get started. So yeah, thank you all for joining. Thank you, Eric, for the introduction. My name is Derek Stenclik with Telos Energy. Going to be going through this presentation alongside my colleague Aaron. Like Eric said, this is the outcome of a task force that met over several months, really thinking about how can we how and why should we be thinking about wide area assessments, continental, interconnection-wide, and continental scale resource adequacy assessments. So while you're going to be hearing from myself and Aaron over the next 40 minutes, this really is an outcome of a very collaborative task force and stakeholder process that really we try to get a lot of views from folks across the country, whether it's from ISOs, utilities, researchers, consultants, you name it. I think really one of the benefits and value that ESIG can bring in this type of space is try to get some of that consensus-driven approach, or at least collaborative approach to some of this work. So you can see the QR code here. If you want to go grab the report, if you just Google ESIG wide area assessment, it'll pop right up. And we'll get going into it. So first, I want to kind of peg where we are in the process of the ESIG Redefining Resource Adequacy Task Force. So for those of you who've been following along over the past few years, thank you. And special thank you for folks that have actually participated in the task force. A lot of great work has come out of this collaboration with ESIG. Started in 2021 with the Redefining Resource Adequacy for Modern Power Systems, which really talked about the fundamental changes underway in the industry and on our power grids that require us to look at resource adequacy differently, and things around chronology and correlation and other drivers around weather and how we need to approach RA differently. We followed that up with two quick reports and task forces, one on capacity accreditation, so thinking of things like ELCC and how we use some of those RA mechanisms and capacity accounting mechanisms for our procurement of resources to make sure we have enough resources and are procuring the right resources. Third report in the series was around new reliability criteria. So where did the 1 day in 10 loss of load expectation come from? What are the benefits? What are the limitations? And what are some alternative considerations we might think about when we're designing or determining whether or not our resource portfolio and our system is adequate? And then this is the most recent, kind of following those first three reports, just released last week, as Eric said, really around wide area assessments. How can we take all of these lessons learned, and what might the benefits be if we expanded the resource adequacy analysis to look at interconnection-wide, multi-region, or continental scale probabilistic assessments. So kind of going back to that first report, why are we talking about transmission and neighboring grids and wide area assessments? If you go back to that first report, we tried to lay out 6 fundamental principles around resource adequacy. And you can see those first 3 reports checked off 4 of the 6. And this 5th one here around neighboring grids and transmission are a key part of the resource adequacy challenge. Most of the time when you see some work around whether a utility or a system operator, ISO is evaluating their resource adequacy, how they evaluate their neighbors, or if and how they evaluate their neighbors in that assessment will fundamentally drive the resource adequacy outcomes for that region. And so it's a fundamental key consideration. We wanted to spend a very focused approach on that as part of the task force. We'll have a little bit more coming out on number 4 there, sneak peek to the large load task force that ESIG is putting together, and we'll have some work out there shortly.
Hey, Derek, sorry
Yeah.
to interrupt. There's a little, I think there might be a pop-up on your shared, yeah, if you're able to X that out.
It looks like I'm sharing videos. Okay, why can't I get? 1 second here. Try that again. All right, how's that?
Yep, it's not there. Perfect. Thank you.
All right. So you're going to hear me talk and Aaron talk quite a bit about wide area assessments. So what is a wide area assessment? Part of what we wanted to do in the task force is define what that means and how it relates to other assessments that you've seen in the industry. So we really broke it down into local, regional, and wide area. So throughout this presentation, throughout the report, we try to be very cognizant of this terminology. So a local assessment is a resource adequacy assessment that's conducted by one utility or one ISO or one load serving entity, basically evaluating their resources, their load, and their portfolio to determine whether it's adequate. So an example of that might be PJM's resource adequacy analysis, or New York ISO's resource adequacy analysis, or Georgia Power's resource adequacy analysis. Right? The idea here is one entity that's responsible for resource adequacy for their service territory. A regional assessment is where you start to see collaboration and coordination of one system operator with their neighbors. So an example of this might be some of the ERO processes like NPCC, the Northeast Power Coordinating Council, that looks at resource adequacy of Ontario, New York, New England, and Quebec together. While it's made up of 4 kind of independent system operators, independent jurisdictions, they collaborate and they share modeling, they share data, they ultimately collaborate and coordinate on how they model one another in their assessments and what interregional transmission looks like between those regions. Other examples might be WEC, who does a regional assessment of the West. CERC does regional assessments. So really what we're looking at here is 2 or more jurisdictions or local entities that are coordinating amongst one another and doing one probabilistic RA assessment. And really what we define here as wide area is now kind of expanding that out further and looking at interconnection-wide or really continental scale assessment that spans multiple regional entities. And it's at a geographic scale larger than a typical weather system. So that was an important piece of this. We do see some regions, you could argue MISO, for example, is a very wide geographic area, but it's only one local planning region, it's only one planning entity, and you can see weather kind of come across MISO and hit the entire MISO footprint at one time. So a couple things there, multiple different jurisdictions and entities, and a geographic scale that's larger than the weather that's hitting it. And really why we're interested in that is looking at interregional transmission and adequacy interactions across those jurisdictional boundaries. So great example of this, while we're seeing examples crop up, certainly in North America, Europe has kind of established this process over the last several years. Europe is doing the ERA process, the ERA, European Resource Adequacy Assessment. Really great example of a continental scale assessment. So it's a probabilistic resource adequacy assessment for the entire ENSOE interconnected system. It looks at 40 transmission system operators across Europe, representing 36 different countries, and they all coordinate to do one wide area probabilistic resource adequacy assessment. It looks out 10 years to look at the resource adequacy of the European system. They have detailed continental-wide weather simulations, so climatological and weather data across the entire continent, and there's a level of collaboration. Now, key thing, we'll get to it later in the process, it doesn't mean that Europe is doing a single centralized planning process. What they're doing here is while each member state and each TSO might have their own local planning process, they also have this layer of coordination and collaboration across the continent. So a very important thing here, not trying to say we should be doing top-down centralized planning for the entire continent or entire country, but rather this framework that can allow both local jurisdictional assessment and the wide area collaboration and coordination with neighbors. So we'll touch a little bit more on the details of this throughout the presentation, but definitely want to highlight this. People can go take a look at the report. I'll also highlight Ralph, Marlene, several other folks from ENSOE were a part of this process. A lot of lessons learned and lessons shared from the work they're doing in Europe. So why should we be considering these wide area assessments? Why not just look at a single region, a single ISO? Why isn't that enough? What are some of the reasons to look at wide area assessments? So the first, really, and this is somewhat ranked. We did some polling of both the task force and a few other venues of why some of these propped up where they are. But interregional transmission planning, obviously, you can't really do that if you're not doing modeling at a wide area, right? If you're only modeling one region, you're by definition not evaluating interregional transmission options, and so this is a mechanism to do that. Second is scenario consistency in local and regional planning. So this is a really important piece here. Again, not trying to replace local resource adequacy work or local planning in any given utility or ISO, but what we want to do there is when a utility or ISO is doing their planning, let's make sure they are consistent and aware of what's happening in their neighbors. We know that the adequacy of any one region is going to depend on things happening around them. And given the pace of change, both on changes in load, changes in generation, changes in retirement, we know it's really critical for any one utility or ISO to know what's happening around them. And so that's kind of bring in those scenario consistency in the local planning, but also bring in neighboring system visibility for number 3. Again, assessing policy impacts, number 4. So policies we know are not beholden to one utility or one ISO. Policies will affect wide areas, and they'll affect both at the national and regional level. 5th is around assumptions around external assistance. What we've seen in kind of doing the literature review, every ISO, every utility has some assumption in their resource adequacy analysis or in their reliability analysis, or even in their capacity market and procurements of what's going to be available from external regions. Now, oftentimes that is sometimes informed by probabilistic resource adequacy analysis, but sometimes it's just a heuristic. And so this is a mechanism to make that work a little better and give more insight there. 6th is around extreme weather event evaluation. We've seen recent weather events that are spanning the entire interconnect or wide area at a certain time. So this is really the process. When we think of heat domes that have really hit the entire Western interconnect, or Winter Storm Uri, Winter Storm Elliott, some of these big disruptive storms, they tend to affect regions much wider than some of those local and regional assessments. And then lastly, just using this as a mechanism to promote methodological and metric alignment. To the extent that we can all be doing these wide area assessments, we can get consensus around the right types of metrics and methods to make that work. And who should be involved in this? So we talked about why, but who who is affected by this. So we kind of created this collaborative view here of a few different entities. So obviously state and local regulatory entities, whether this is state commissions or local regulatory entities that are kind of overseeing the ISOs or utilities. Federal entities, so, you know, clear thing here is ultimately resource adequacy is in the purview of the states in most places. And so while not charged with ensuring adequacy, federal entities like FERC or others, or DOE, they can support by advancing common data sets, establishing modeling workflows, coordination across the entities. There's still a role there for the federal entities, even if they're not ultimately responsible for resource adequacy. Reliability organizations, so in this case, NERC or NTOE or folks, they're really the folks that are going to be administering the process, coordinating across the regional entities and utilities. The utilities and ISOs and RTOs, they're going to be providing data, assumptions, modeling methods, and then just overall stakeholders. There's a lot of other folks that can be involved, including customers, developers, NGOs that have a role. So with that, I'm going to pass it over to my colleague, Aaron, to go over the next several sections.
Yeah, thanks, Derek. So I'm going to be jumping into specific data needs for wide area assessments. And I imagine there's a bunch of modelers on the call. And so you know as well as I do that our models are only as good as the data that we have underneath them. So if you can go to the next slide, please. So we have several categories of data that are really essential for wide area resource adequacy assessments. The first and second on this list really relate to network topology, thinking about how we're representing the different regions and sub areas within the continent or within the interconnection that we are modeling, and then the transfer capabilities between them. So really thinking about how much can we reliably import from one region to another, both looking to set those transfer capabilities in a robust way, and then leveraging wide area assessments to really provide additional insight into how other local and regional entities can think about that. Of course, we need to represent the power and increasingly energy storage within the system. So representing the future capacity mix, deciding on the relevant study horizon. That can include supply side resources, but also demand side resources such as flexibility. Weather data is essential. And so we like to think about the 3 C's of weather data that is covering a wide area, correlated, and consistent. And I'll be diving a little bit more into what we mean by those in just a couple of slides. And then finally, thinking about representing contracted resources and transmission versus their physical location. And because we don't have a slide on this specifically, I want to spend a little bit more time here. It's common in resource adequacy assessments to include the specific locations of resources, for example, within a region. But it's also important to think about the role of contracts and, for example, firm capacity commitments, because we may have a resource that's in one or a utility that's in one region, but contracting capacity from a resource that is in another region. And this has implications for whether and how much we might expect unserved energy to show up. So if we just look at physical location, we may see unserved energy showing up in a region. But if we were to account for contracted capacity that may be coming in from another region, that may reduce or fully mitigate that unserved energy. So really important to think about the impact here and thinking about how we can integrate this contractual layer into this type of modeling. Next slide, please. So I know Derek had a pretty detailed slide about the various stakeholders involved and mentioned, really that wide area assessments are an opportunity to really drive better coordination and collaboration across entities. And I think data sharing is just a really great example of that. And this is essential really in both directions. So thinking from local entities, utilities, ISOs, data flowing up to regions and ultimately up to reliability organizations or government entities, think NERC, think ENSO-E. And this sort of bottom-up flow of data can include regional or local planned resource additions and retirements, load forecasts, interregional transmission limits, and as I was speaking about contracting, contractual information such as jointly or remotely owned resources. These are the utilities that are on the ground. They're developing the IRPs. The ISOs are running the capacity markets. They have that more detailed, granular insight and are very well positioned to collect, aggregate, and ultimately pass that data up, whether to regions and regions up to the reliability organizations. But I think it's also just as important to think of how that data can flow back down and the unique types of insights that can come from the top-down direction. So that includes aggregating the various regional and local data, so aggregated resource additions, retirements, and load forecasts. National organizations are well positioned to provide analyses or insights on interregional transmission limits, which we'll talk more about. For especially the wide area continental size data sets, again, the more national scale organizations are well positioned to provide that data. And critically, a common set of scenarios that can both help facilitate some of the more regional or local analyses by allowing those planners to draw upon this common scenario set, but also help regional or local plans be more interoperable and to be able to more easily compare outputs when they are based on and running off of some of these common scenarios as well as data sources. And we can go to the next slide. All right, so I want to talk a little bit more about transfer capability and transmission constraints. And just recognizing that there are several different options for calculating transfer capabilities. And as we go down the list here, increasing in complexity, most simple is maximum observed flows. So looking at historical data, see how much power is transferred between regions, and using that to set transfer limits within an RA model. Most simple, but definitely has some shortcomings. For example, the system may have evolved since compared to historical data. If stress events that are reflected in maximum observed flows weren't fully stressing or fully loading the transmission network, there's a risk that these could underestimate flows. So need to keep those trade-offs in mind. A little bit more complex is simplified DC optimal power flow, or DC OPF, which uses DC power flow assumptions in order to simplify linear optimization of dispatch and power flows throughout the system. This is more computationally efficient and tractable than option 3, which is a full AC power flow analysis, but doesn't capture some of the physical system dynamics, such as voltage constraints, dynamic stability, or contingencies. For that, we need to look towards option 3, which is the most computationally expensive, but also the most comprehensive. That's a full AC power flow analysis. I think I'd say another shortcoming here is really can only evaluate one snapshot case at a time, but does capture the underlying physics of the system and is the most comprehensive. Our figure on the right here from the NERC Interregional Transfer Capability Study, or ITCS, the AC power flow analysis was used in determining these transfer capabilities. So really the context matters a lot when deciding on approaches. the types of questions we're asking, the type of data we have available, the amount of computational resources that we have. And in fact, there is a role for hybrid approaches. For example, we may use option 1 or 2 to evaluate maybe a wide number of scenarios or snapshots, and then can zoom in with more detailed AC power flow analysis for validation. I think we can go on to the next slide. So we've set our network topology through one of those 3 methods. Now we need to figure out how we want to represent the generation, storage, and demand side resources. And here, as before, there are several options that are really going to depend on the context, the data availability, and really the aims of the analysis. So just to quickly go through these, we can look towards at the interconnection queue, leverage proposed projects that are in the queue, but requires us to make some determinations on how likely those projects are going to materialize. And I'm sure everyone on this call is well aware of some of the interconnection backlogs and log jams. Means that we really need to be deliberate in how we set those boundaries. An example here is the NERC long-term reliability assessment has multiple tiers, tiers 1, tier 2, tier 3 resources that represent various levels of project progress or different criteria for projects on the interconnection queue. Option number 2 is to take really a centralized planner's perspective and to perform top-down capacity expansion modeling that creates a system optimal set of resources to use in a resource adequacy assessment. This is helpful in that it allows us to really be in control of the assumptions and methodologies that we're using for that, really ensure that those are consistent. But this approach doesn't really reflect how planning is really done in the United States, which is through local planners who all may have their own assumptions, methodologies, and processes. And that brings us to option number 3, which is bottom-up reporting, which involves aggregating utility IRP plans where they're available, as well as projected resource mixes from other resource assessments, regional assessments. Of course, this type of data isn't available from all jurisdictions. IRPs typically do a good job of laying out forward-looking plans, but those aren't available in many restructured regions. But really captures, I think, the way that planning is done with these more localized regional plans. And on the right here, we see just one example of an effort from EPRI, which aggregates regional plans and is able to take a higher level, regional and national level forward-looking view of planned additions and retirements. Next slide. Okay, last but not least is the weather data. And so again, we have the 3 C's covering a wide area, consistent, and correlated. I know Derek has already talked about the first here, which is we know that at the continental and interconnection-wide scale that weather is really big, and polar vortex, a heat dome, can really cover much, if not most, of that geography. So we really need to be able to reflect that in the model, ideally drawing these weather events from a consistent shared interconnection or continental scale data set. That data also should be consistent. So data for weather, solar irradiance, wind speed, temperature-driven loads should be consistent in time and space, and ideally be based on observations from a physics-based meteorological model. I think it's important to point out that even from a single model, if it's run, say, by different entities or utilities, they may be using different assumptions to parameterize those models. And so it's not necessarily as simple as just saying, same model, same weather model, we can just combine this data. No, we really need to check to ensure consistency in the parameters. And that, let alone when they're multiple different weather models being used for different weather data sources. So really making sure that they are consistent, that they're using consistent assumptions so that we can create a unified wide area data set from them. Finally is correlated, and this is absolutely essential. Weather-dependent inputs are temporally aligned and spatially correlated across the assessment footprint. That means capturing the correlations of weather events that correlate wind and solar irradiance, for example, or temperature and load. Also capturing the impact of temperature on ambient D rates or outage rates. Making sure that not only are we considering these weather impacts, but that they're all correlated across one another. And our figure on the right comes from a resource and adequacy analysis with using the grid path RA toolkit, which is a great example of an interconnection-wide study that I think does a good job at covering these three C's. Next slide, please. All right, so we've done the hard work of making a awesome data set. We've put together our wide area resource adequacy assessment. We run the model. Now comes the fun part of actually making sure that it is used and useful and really driving better planning and useful insights. We're going to talk about three ways that they can drive impact. Number one is serving as a reliability backcheck on regional plans and to validate regional assumptions on market assistance. Number two is for interregional transmission evaluation and accreditation. And finally, helping fine-tune and creating better assumptions and processes around capacity sharing across and between regions. Next slide. So this slide shows that there is a variety of different options for incorporating interregional transmission in RA assessments, whether those assessments are at the local, regional, or full interconnection level, ranging from modeling an isolated system without consideration of neighbors, modeling simplified assumptions of import limits, such as using a proxy dummy resource, modeling neighbors, but calibrating them to a specific RA criterion, such as the 1 day and 10-year loss of load expectation, using neighboring resource mixes without that calibration, and then finally modeling the full interconnection. When we're talking about wide area resource adequacy assessments, we are all the way on the right here. And I think this is a great example of seeing the range of different configurations here and how by modeling the full interconnection, we can get really helpful data sets or insights from the analysis that can trickle down to those local or regional assessments that may be using a more simplified approach, but can still rely on some of those insights from the full interconnection model to, for example, parameterize a proxy import resource or characterize the resource mix of a neighboring system. So really having that data flow down. Next slide. All right. So here is an example of how different ISOs and RTOs assume different levels of imports in their resource adequacy models, and how those assumptions from those models drives real planning outcomes. For example, translating into capacity market requirements. We can see that these vary quite widely across the RTOs. So on a relative basis, external assistance assumptions in resource adequacy assessments is the lowest for SPP, MISO, and PJM, despite the largest interconnections to neighbors. And we can see that on the left. But we can also, when we look at the right, which is these RA assistance assumptions reported as a percentage of maximum historical transfers, a really wide range, 30 to 63% of those historical transfers. And we're seeing the highest in SPP, NISO, and ISO New England, really reflecting a more sort of less conservative, more aggressive approach for thinking about how much reliance there can be on neighbors. tying this back to wide area resource adequacy assessments is that these analyses can provide really valuable insights for helping fine-tune and calibrate these numbers and these assumptions for external assistance, including through assessing multiple scenarios, through having robust data sets that can really give planners confidence in setting these values. And I think that's a huge value add. I will turn it over to Derek to talk about the next two options and any other insights here.
Thank you, Aaron. So what do we do with all this information? If we think about how we model our neighbors, what are the options of taking that information from the assessment and actually translating it into capacity procurement, whether that's in a wholesale capacity market, or if it's in the case of an integrated resource plan for an individual utility or ISO. Ultimately, we want to take the information from these probabilistic wide area assessments and help inform the resource procurement. And there's three ways to do that. We have this kind of schematic off of on the left for three options. And the important thing is we want to make sure these are not mutually exclusive to one another. You can use these in conjunction with one another. So the top in the light blue here, we have kind of using this information to evaluate contracted resources and firm transfers only. So this is maybe a region or an ISO or utility wants to only count external resources that are contracted and have firm transmission access to sell into the market. That's kind of the most conservative view, is require contract, require firm transmission to make those resources deliverable, and then you can use that to offset local capacity within the ISO or within the utility. So that's that is a route that several regions take. The next step in allowing some level of non-firm market assistance or interregional transmission to count towards capacity is to do so by reducing the planning reserve margin requirement. So you would use the resource adequacy assessment, and we see utilities and ISOs do this, where they'll run the assessment, they'll calculate what it takes to get to 1 day in 10 LLE or another reliability criterion in the region. They'll run that first without any non-firm external assistance from neighbors, and then they'll run it again with the external assistance available and imports available. And then sometimes they'll do different variations along the way. And they'll use that information from the probabilistic RA assessment and say, well, maybe our reserve margin requirement would have been 20% without that external assistance, but given kind of the probabilistic analysis that we did, we can consider, or we can use a planning reserve margin of say 15%, and that means we're saving 5% of our peak demand in capacity, and then ultimately saving money for the existing ratepayers, but acknowledging that we're doing so by assuming that external assistance will be available when it's needed. So we see most regions have, whether it's utilities or ISOs, most regions are doing some level of this adjustment to the planning reserve margin requirement or to the capacity market requirement, load obligation, based on some amount of non-firm external assistance. And we really see this as a big opportunity for these wide area assessments to really further define, refine, update, and give technical basis to those adjustments that are happening. And then lastly, the third option, just kind of treating interregional transmission as a supply size resource, I think is kind of most applicable to controllable DC ties. So this would be like a transmission resource kind of offering directly into the market or into the procurement, and being accredited alongside some generation resources. And again, we can use this wide area probabilistic resource adequacy analysis to come up with that accreditation. So just like we assign ELCC to wind, solar, battery, and a gas plant, we can do the same thing for that external non-firm assistance, especially in the case of some DC ties where they're controllable and very measurable. We can do that both in the conventional transmission planning process, or we can do it kind of in this market approach. So again, there's differences both in conservatism, kind of top contract only being the most conservative, maybe say the orange interregional transmission of supply side resource, kind of most least conservative or kind of balancing both cost and reliability a little bit more. So example of that last approach, the intertie accreditation, if you look to the UK, and again, big credit to the NISO folks for being a part of this task force and sharing their lessons learned and how they approach this in the UK. For each of the DC interties between the UK and neighboring Europe, the process for National Electric System Operator in the UK is to use that wide area probabilistic resource adequacy assessment, so evaluating all of kind of the neighboring continental Europe, and then assigning an ELCC, or what they refer to here as a D-rating factor, based on the availability of those interties during resource adequacy events. It's really accrediting transmission just like we would other resources, and this is what gets offered in and used into the capacity market mechanism in the UK. So I'll briefly go over the next slide. So we talked a lot about the modeling approach, and Aaron covered some of the data. We talked about the why. Aaron talked about the how. I just kind of covered what we might use that for. And then here I'll talk a little bit of like what it would take to implement this in practice at a wider scale. Again, using these wide area assessments to inform actual procurement and capacity sharing between regions. Again, I'll revert back to pointing to Europe as an example. So I talked about the European Resource Adequacy Assessment. That's the probabilistic assessment that ENTSO-E performs. Now, how that gets used is really comes down to this EU regulation around the internal market for electricity. And that regulation, the ERA is one component of it. That's, okay, every year ENTSO-E will perform an assessment, and then how that gets used is really the key points here in parts of the legislation. And so again, one is adequacy assessments are performed both by member states. So each member state does its own assessment, and then ENTSO-E does the European-wide assessment. If there is a deficiency in either one of those, basically member states have to come up with an implementation plan. Like, what are they going to do to resolve that resource deficiency or the resource adequacy risk? Now, again, it's not, if you get a failing grade in one or the other, it's not like a region is required to go procure more resources. They just have to put forward a plan or explain why there's a distortion that has to be resolved or what the basis of it is. So again, by no means, I think really important if we think about applying this to the US, by no means is that wide area assessment being used to mandate any type of resource procurement at the local level. Fourth is each region, each member state is able to select its own reliability standard. We talk about that a lot in actually the resource adequacy criteria report that ESIG put out last year. And 5 and 6, I think, is really interesting. Number 5 says that capacity in any one of those member states has to be given an equal opportunity to compete with local resources. So if there's a resource in France and it wants to participate by selling capacity into Germany, it has to get the opportunity to do that up to what is referred to as maximum entry capacity. So it allows, not only allows for capacity sharing across regions, it actually requires the ability to, you can't exclude external resources in an unfair way. The 6th, also interesting, a capacity provider, a resource, a generating resource, can actually sell capacity into more than one capacity mechanism at the same time, as long as the expected availability of the interconnection and the concurrence of the stress. So when resource adequacy risk shows up, as long as those don't occur at the same time, they can do that. I think another important thing, especially when you think about resource adequacy risk that might occur at different times in different places across a really large interconnection. And I'll just highlight quickly that RAP is starting to do something similar with a wide area resource adequacy assessment, and then using that to inform potential capacity sharing across the region, and really using that wide area assessment to harmonize the ELCC and accreditation and the reserve margin requirements across each of the member utilities. So I think a good example of starting a process similar to maybe what we saw in Europe in some respects, obviously unique for the West. And then what might that look like if we took that European model, applied it to the US? Again, by no means are we saying this should supersede or replace any local planning at utilities or ISOs, but certainly a framework that could go on top of what we have today, similar to what is going on in Europe. We lay that out in the report, and given the time, I'll kind of skip through this. And then I'll conclude. NERC was also a participant in the task force, and just want to highlight some of the changes they have going on in terms of actually implementing some of these wide area assessments and trying to get a process going similar to what's outlined in this report and what's happening in Europe. So a lot of you are familiar with the NERC long-term reliability assessment. Historically, that was kind of the annual and seasonal reserve margin analyses that you're probably accustomed to. That was also included regional Prob A studies, so probabilistic studies at the region. So NPCC and WEC and CERC and MRO were all doing probabilistic studies for their regions. And just last year in 2024, NERC did the interregional transfer capability study that looked at energy sufficiency and energy considerations across the entire North American system, and looked at transmission transfer capability between those. And that really set up what is now kind of currently underway, this North American adequacy assessment, an interconnection-wide assessment that they're just piloting now in 2025. Looking at full probabilistic resource adequacy analysis of the North American system, an Eastern Interconnect model, Western Interconnect model, and ERCOT model, again, evaluating probabilistic RA across a really wide area footprint. So pilot study for this year. The plan is for full implementation in 2026. And again, I think working collaboratively with this ESIG task force when they were scoping out that new approach. So certainly making great inroads there in applying similar work to the North American system. And with that, I think Aaron and I will both pop on the video here. I'm happy to follow up with anybody offline, but we've got 10 minutes here to go into the Slido and any questions from the participants.
Awesome. Thank you, Derek and Aaron, for the presentation. So right now we have 2 questions, and so I encourage folks to add some in there if you have some. I can add a few of my own if we do have time. But let me ask the first one here, kind of around modeling versus reality during these critical time periods. Of is that something, if in these studies, what you consider as the capability of transfer across regions, and sort of how neighbors are assisting during certain types of critical time periods, how does that differ from whether they're actually able to provide that assistance during these time periods? How do you sort of capture that within this modeling?
Yeah, and I saw that question come in, and it came in early, so hopefully we addressed some of that as we were going. But I think fundamentally this is the role of that wide area assessment, is to try to get the assessment and the model as reflective of those realities that you're referring to, whether those realities are, hey, your neighbor is seeing the same severe weather that you're seeing, and so maybe we can't rely on them. So let's make sure that's showing up and reflected in the model. Or maybe the transfer capability from that neighbor, the transmission system is congested and we can't actually transfer all of those imports from the neighbor. Well, again, let's try to get that reflected in the model. So I think the key thing here is this is really the use case of that wide area assessment. It's just try to get those realities in the resource adequacy simulation of the region. As opposed to what some places do say, which is just come up with a heuristic or say, we're only assuming 500 megawatts from neighbor A, or we're going to limit the contribution, or we're going to say, we're going to assume we have to be completely self-reliant because we just aren't 100% sure. So I think really the goal here of the wide area assessment is to try to reflect those realities, do it in the probabilistic resource adequacy framework, and use it to inform what should that allowable import be. Yeah, hopefully that answered it. I'd say maybe from an real quick example, like PJM, they have a constraint that models a maximum import of 3,500 megawatts into the PJM during RA events, and then they allow 2,500 megawatts to count as firm capacity to lower that planning reserve margin requirement. And so like what this wide area assessment approach would do and is inform what those numbers should be. And that's something PJM is doing, and something we could kind of expand to other regions.
Great, thanks, Derek. Next question is whether there's a good data overview on inputs like planned and unplanned outages and other data associated with that. I guess GAD's data, I don't know if there's a difference with the data that you'd use from the interregional versus a standard data that's being used for an RA assessment.
Yeah, I guess in terms of critical inputs, I think that's hopefully one of the benefits if we do get a process of wide area, kind of interconnection-wide, continental-wide modeling, is some of those data sets will have to be developed for this type of study. Ideally, those can be made available. So good data input, like on what's needed, certainly continental scale weather data. So wind speeds across the country, and again, what Aaron talked about, time synchronized and correlated across the entire footprint. Wind speeds, solar radiance, temperature that is informing the load, weather dependent outages, so outage rates across the country that are correlated. We know those thermal outages, especially on the gas network, can be correlated. We want to make sure we can get that. So that's definitely a data gap and a data need, and something I know NERC has been working on improving. Anything else you want to add there on the inputs, Aaron?
You're on mute, Aaron.
You're on mute, Aaron.
Yeah, I think creating these data sets is a constant effort from the industry, and I think a way that we're kind of framing not only the analytical value of the wide area assessment, but alongside that is the ability to really create, we're calling it like a clearinghouse of data. And so I think by having these flows of, from the local to regional to national and vice versa, that can serve that, and certainly outages and other operational data to the extent that it's publicly shareable can be part of that.
Great. I'm going to sort of maybe expand the next question a little bit and ask, in the interregional or wide area assessments, and there is a lot of this contracted external capacity that's associated with different regions. Is there different ways you have to model those contracts? In other words, like, is there a modeling feature with the contracts, or you sort of, the question was, do you represent it in, its physical location or not? And I think I know the answer to that, which you can share too. But I guess just more broadly, is there a difference to how you model that within the wide area assessment?
Yeah, so
model contracts.
Yeah, my recommendation here is to, especially when we think about, if you're just modeling a single utility, then, well, if you have this external resource, sure, just cite it kind of in that one footprint, and it doesn't really matter. But I think when we think about a wide area assessment, and we're trying to evaluate all of the regions simultaneously for their adequacy, this question comes up a lot. My recommendation is to cite the resource where it's physically located, because we want to make sure we're accounting for the transmission capability to get that deliverable. And we want to make sure we're not double counting capacity by sliding it into transfer capability, by sliding it into the region it's contracted. So my recommendation is to put it in its physical location. Now, where that becomes problematic is when you run the model and everything's where it's physically located, maybe you have a deficiency, like when a loss of load event shows up in a region, you say, oh, well, if it shows up in two regions simultaneously, like who gets the quote unquote blame for that? Like who gets the loss of load event? It might actually be one region's fine because they've contracted for a resource in a neighbor. And so they actually are okay when another region might be deficient. So where it gets to be problematic is when you have kind of loss of load events popping up in multiple regions at the same time, which certainly can happen. You think of like Western wide area heat dome affecting the entire Western region. California, for example, has a lot of external resources that they're contracted with in Palo Verde and Hoover and Intermountain and other places. And how you do that accounting if there's loss of load in multiple places at the same time. So I think that's certainly something you can adjust for by just adjusting how you model contracts and how you calculate the loss of load and who gets the ding for the loss of load, if you will.
Yeah. I might squeeze in one more question. I know we only have 1 minute left here before the top of the hour, but I'd be really interested, especially having the some of the folks from the ERA involved. So obviously in the US, there's so many differences with like, you know, how accreditation is done between in different regions, and like what do they consider a loss of load, and like different metrics. And that to me, you know, with the stakeholder debates that often happen on like the market stuff, it's like, man, you can't get anywhere. And I wonder, like, did you learn anything about how they like come up with these consistencies across the European assessments, or any kind of recommendations for how you can agree on things with, you know, sort of how you would do this with so many differences in place today with each regional or with each, you know, local system adequacy assessment?
Yeah, I think, yeah, in the European context, there's each member state will have its own capacity mechanism, where one country might have a capacity market, one might have kind of centralized procurement. So there will still be significant differences in the actual market implementation, accreditation, things like that within a market and within a member state. But I think the wide area assessment does, at least at a continental scale, viewing reliability, looking at 10 years, they've kind of made some of those methods consistent, and the metrics in terms of measuring adequacy consistent. And the member states are still free to do the analysis however they want for their own assessment. I do think by harmonizing some of the process and methods and metrics at the continental level, it's just going to, by nature of it, trickle down into the member states, and it's just going to drive consistency that way. We see it even here in the US, like, why do we use 1 day in 10-year LLE? Well, most people just say, well, they point to the neighbors and say, well, that's how these ISOs are doing it, right? And that's how these utilities are doing it. And when you drive that consistency, it might not be the right answer, but at least by having that wide area assessment, I think by the nature of it, you will get more consistency even in the local assessments, because they can point to the broader process. So hopefully that actually helps make some of these more harmonized. But again, the important part is each local utility, each ISO will still have the ability, or would still have the ability, to make their own market rules, make their own accreditation. But I think it would drive to more consistency, even if not perfect consistency.
All right. Thank you, guys. Yeah, I think we're at our time here. So appreciate everyone for attending today. Look forward to seeing everyone soon, including in less than 2 weeks in Philadelphia at the ESIG Fall Technical Workshop. Yeah, just a note that all information on webinars can be found on www.esig.energy under events, as well as in the newsletters and informational emails. So Derek and Aaron, thank you so much for your time, and looking forward to looking at the report in more detail. And yeah, we'll see you all again in the near future. Thanks.
Thank you all.